As David introduced me, my name is Bob Martin. I came over from the Atmel acquisition that Microchip bought at Atmel in 2016. But I've been working closely with Arduino for 14 years now. The legacy or the background on this is Atmel made, or still makes, Microchip now makes the Atmel 328P, which is the microcontroller on the Uno R3. And we also make some other microcontrollers that are well received out in the makerspace, the SAMD51s and the 21s that Adafruit sells that run CircuitPython, and there's some MKR boards and some Nano boards that Arduino still sells. So what I'm going to talk about today is, as the slide deck suggests, is a update on what we're doing, some of the new stuff. I'm going to be focusing on the new 8-bit AVRs. Since in the education space, the 8-bits typically are easier to learn how to program. Even with the Arduino shell on it, we still have, the 8-bit space is still very much alive, although all the cool stuff with RF and whatever and Wi-Fi and Bluetooth tends to be migrating to the 32-bit stuff, which we support as well. However, the new AVRs, which are now are Arduino compatible, for those of you who want to stay with a simpler programming environment, or again, power consumption, there's a whole bunch of reasons why you'd want to look at some of the new AVRs, and I don't have enough time to go into them now, but I'm going to cover some of the new stuff on the new AVRs and then show off a new eval board that we have. So we took the AVRs, what we call the classic line of the AVRs, again, the Mega 328P, and it's the biggest older brother it has is the Mega 2560, which is on the Arduino Mega 2560. That's the big 100-pinner. What did we do? We made them better, faster, and stronger over the past couple years. And we released this, as I said, a couple years ago, but the pandemic kind of eliminated my ability to wander out and tell people about it, and now we're just getting back into the swing of things. It's the same core, which means that the compiler, the free GCC toolchain, still absolutely works. We didn't change anything in the instruction set. What we did was we increased the performance, we added more memory, we made it run faster with improved peripherals. For example, single cycle IO. If you dig down deep into the guts of a microcontroller, being able to change a pin on a single cycle is an important thing now, to be able to keep up with timings and things like that. We've improved the analog to digital converters. They have more bits of depth, and we can now set them up automatically to deal with multiples. If you take multiple samples in a row and then average that result, you can get rid of noise a lot easier, and you don't even have to think about it. And one of the more significant things, especially in the makerspace, which makes these parts really attractive, is one of the reasons the Mega 328P was used or adopted by Arduino is it had the self-programming feature, which means they could use a serial bootloader, and the bootloader would listen over the serial port, and then if it caught the right command, it would go, okay, I'm going to program. I need to now tell you to self-program yourself, and that was one of the significant features of the AVR that allowed Arduino to do that, such that people learning how to program only needed a serial port. You just needed a USB cable. Previously, in embedded programming, you needed an expensive programmer debugger, which made it kind of out of the reach of the hobbyist space. We took that to heart when we designed a new debug interface a programming and debug interface on the new AVRs. It's called UDPI, and it's a single wire. And we open sourced the programming algorithm. And all you need to program one of the new AVRs now is one of those FTDI USB serial converters and a resistor. And we have a free Python utility that allows you to take compiled Arduino sketches and program them directly, so you don't need bootloaders anymore, so you get that extra memory space. Because for the cost of a $3.95 USB to serial converter and a 1K resistor, you can program the part. We added more accurate clocks. We had, as I mentioned, faster clocks. Some of the parts can run up to 24 megahertz. There's a split between 20 and 24, depending on the complexity of the chip. That's just kind of way the chip design game falls sometimes. But the important improvement on that is the older AVRs, if you wanted to run them at higher speeds, you had to use higher voltages. The 328 and its family, if you wanted to run it at 16, you needed to run it at 5. Technically, you didn't. You could run it at 3.3 volts and still run it at 16, but if you got up to the higher temperature limits, it would start failing. These parts run full speed from 1.8 volts to 5 volts. Okay? You're not limited by your processor speed or your clock speed by what voltage you're feeding it. We also added internal 32 kilohertz oscillators. So if you want to go into low power mode but still stay awake, you can switch dynamically to a low power internal RC oscillator to keep basic time. And then, I mean, it's not super accurate, but it's for a lot of maker things, if you want to wake up every minute, it's more than perfectly accurate to wake up out of low power mode and then go back, switch over to the high speed clock, and then do what you need to do and go back to sleep. And you can tell when the clocks are properly, before you switch over to the high-speed clock, you can tell if the high-speed clock's ready. So we have a bunch of safety features and clock fallback, which is what clock failure detection basically means. So yeah, so I said faster I/O, atomic bit sets. That just means it's one clock cycle to set a bit high or low. 12-bit ADCs, I mentioned with slightly faster data collection, and the auto sampling is that, again, that auto taking samples, adding them together, and then you just divide the result, and you have a result that's much more accurate. We also added multiple internal voltage references, which means that we have highly accurate voltage references inside these parts. So depending on the type of voltage you're sensing, you want to pick a voltage reference that's just above the maximum. You've got like 1.024 volts, 2.048, the actual voltage rail, and I think there's another one in there between. The other thing we added is more peripherals. And by being more peripherals, the Mega 328P has one UART. And there was a soft serial library if you need another UART. Almost every new AVR has at least 4 UARTs on it. And these are hardware UARTs. Not only do we have more UARTs, you can reassign the different UARTs to different pairs of pins to adapt to your design. So where this is really important is if you still want to use the old bootloader technique, you can still dedicate the primary UART to the bootloader, but if you want to talk hardware serial to a Bluetooth module or a Wi-Fi module, you don't have to use soft serial anymore. It's an actual hardware UART, okay? So you're not limited you don't have the speed limitations that soft serial does. Some of the parts we have more timers, so you can run more pulse width modulation channels. They're more powerful pulse width modulation. Some have waveform extensions, which make them really good for driving brushless motors. And some of the parts actually have multiple I2C peripherals per package. So you can run separate I2C buses. And where that becomes even more important is the AVR DB and DD series, and I've got the DD up here on a board I want to talk about as well, are the first 8-bit microcontrollers. Believe it or not, 8-bit microcontrollers have been out for a long time that can support 2 voltages on the I/O rails, which means that you can talk 5 volt to industrial things like PLC controllers or NeoPixels or whatever, and then separately powered, there's a separate VCC pin for another port where you can feed in 3.3 volts to talk to a Bluetooth module with all the voltage translators are in the part. And you don't have to bring up either rail in a specific order. If you bring up the 3.3 volt rail and leave the 5 volt rail like dead, it's not going to work, but you're not going to damage anything, and vice versa. It all takes care of itself internally. So that's I've done some interesting designs where it was a smart magnetic, 3D magnetic window sensor, where it had a triaxial magnetic sensor, which prevents people from, for those of you who know how those magnetic window sensors work, it's literally a magnet and a reed switch, right? So the magnet gets to the reed switch, it closes the reed switch. But you can spoof those if you get one like a really strong magnet from an old hard drive and snap it in the window beside the reed switch stays closed and you can open the window, okay? A 3D magnetic sensor, I was sensing the magnetic field in all 3 axes. And so if you tried to spoof it with another magnet, there's no way you could match the original magnet's magnetic field because we patterned it. We created a 3D image of what that magnet looked like. That sensor was operated at 1.8 volts, and I was talking to a Bluetooth module at 3.3. And like I said, as David introduced me, I've got 30 plus, I've been in this business 30, 35 years. That's the first microcontroller project, first 8-bit microcontroller project I've ever done where I've had 2 voltage rails at 1.8 and 3.3. And I didn't need any voltage translators. I could hook up everything I needed and just fed, and I actually used the microcontroller itself to generate off a digital analog converter my own 1.8 voltage source. So it was an interesting thing, and I think that it's going to add this whole new dimension of projects that need to talk to different voltages at different sensors. Sensor manufacturers are, if you look at Adafruit, they always add a voltage regulator to make sure, even though the sensor works at 3.3, you can give it 5 and they have automatic level shifters for I2C at 5. We're getting to the point now where we can make stuff cheaper because sensor manufacturers, the one way to lower power dissipation on a sensor is to lower the voltage, okay? And that's why a lot of companies are moving to 3.3, and that's why this other company moved to 1.8. Again, I'm going to mention UDPI again, the Universal Programming Debug Interface. Again, it's a 9-bit serial protocol. And all you do is take a 1K resistor off an FTDI between RX and TX and take that signal off and push it or connect it to the UPDI pin of the microcontroller. And we have a free Python utility called PyMCU-Prog. I can, if you drop by the Microchip booth, I can show you the website. And that's your programming model, okay? You can just hit a command line, and it's also supported within the Arduino environment, which I'm going to show you really quick. So I'm going to talk just a minute about our newest AVR, then I'm going to roll on to an Arduino example, because all the new AVRs are supported in Arduino, which was one of the key things I made sure happened. We just released about 2 months ago the AVR 64DU32 or 28. This is the better improved, less expensive version of the Mega 32U4, the 16U2. So this has native USB on it. This part's been a long time coming, but I'm finally glad it's here. One of the biggest improvements on it is we've got twice the flash, and we've got it's got more flash and more RAM. It's not only less expensive to buy, it's faster, but it doesn't need an external 12 megahertz crystal to operate USB. It does clock recovery from the USB that's connected to it. It's only a USB device, but that's fine. But we recover the accurate USB clock from the USB connection itself. So you're saving the board space and the cost of an external 12 megahertz crystal to talk USB. Okay? And I'm currently working with the author of DX Core to add the USB stack to it. We're using the Lufa stack. So again, it's all open source. So I'm anticipating that hopefully by the end of the year, hopefully that I will get all the examples running for the Arduino Micro. And so we're supporting HID, which is keyboard, CDC, which is the UART. We'll try and support mass storage. That's going to take a while, and by my mass storage, that means if you snap on if you connect a SD card through the one-wire SD, the SPI protocol, we can enumerate as a USB drive. It's not going to be as fast as a standard SD card, but we'll get MSD or mass storage devices running on it. So the other board. Two more boards I want to talk about. These are what's called a C Nano form factor. And at any of the new AVRs that I talked about, or of the AVR, the DX series, or the EX series, these boards it's a standard pin interface. It's a mashup between Arduino Nano and Adafruit Feather. It's kind of our own footprint, really, but it's in the same ilk of generating a breakout board in a DIP package that's easy to use. They run $15. They have their programmer, they have an onboard programmer and debugger. And the other thing I want to mention is I'm working with Arizona State University to develop a plugin for Visual Studio Code to import Arduino sketches into Visual Studio Code /MPLabX to provide source-level debugging capability on Arduino sketches. And therefore, these boards will support that. So I've taught courses on debugging Arduino. And for people that are developing libraries, this is invaluable because you can actually set breakpoints and inspect variables. You don't have to use serial printf as a debugging tool anymore. You actually have real debugging control. And the other board I'm going to talk about, which I have up here as well, is the Curiosity Nano Explorer. It has a large amount of sensors and displays and actuators and switches, both physical and touch. So it's kind of like a microcontroller lab on one board. We've got, like, again, a micro click socket, a quick bus connector. We're promoting in the education space. It's $95, but you get a lot of sensors for that. And I'm just going to walk through a seriously quick, if I got time, seriously quick demo on the board. All right, so I am going to crack off my PowerPoint. Save. And I pop the font on up of the Arduino IDE. And by the way, if you're not using Arduino 2.x, I would highly recommend you start using it. Arduino 1.8, I know people are very attached to the green and black, but the 2.x interface is superior in almost every way. including the fact that once we get the debugging plugin working for Visual Studio Code, this debug button will start working for the AVR 8-bits as well. This, I'm not going to go through, nor do I have time to go through every line in this example, but this is using what's called the DX core, so it fully supports all the AVR DUs. And the one thing I wanted to point out, I'm using a whole bunch of Adafruit libraries natively. If you look at the header files, I'm using their graphics library, their SSD 1306 OLED library, because that's on the board we put a 1306, an SSD 1306. All the sensors on this board are supported by Arduino, either SparkFun or Adafruit, or by both at the same time. So you can see I'm running a, I actually commented out, this one I deleted it. I'm running NeoPixel. We have our own NeoPixel library because the Adafruit NeoPixel library for the AVRs can't handle how fast we go because I'm running this at 24 megahertz, so their library doesn't know how to deal with a 16 megahertz core, with a 24 megahertz core. This is basically the bitmap we call the meatball, which is, the meatball is our description of the Microchip logo. Internally, it's known as the meatball. I just used one of those multiple image manipulation programs to break it down to a 51 by 52 bitmap. The one thing I'm going to point out before I just show up programming is, remember when I said almost every new AVR's got 4 UARTs? The one UART that's hooked up to the debugger programmer USB converter on those Curiosity Nano boards is actually on major UART 3. And so there's a new method underneath serial called swap, which means pick UART 3 to do all your stuff, but everything else runs exactly the same. Under here, because I'm running with no bootloader, I can go down and actually pick the programmer as a Curiosity. It's called a Nano EDBG. And what I'm going to do is I'm going to just directly upload this sketch via the programmer, not the bootloader. So again, I'm saving memory by not needing a bootloader. Now, we're working on remote bootloaders, because bootloaders are really useful for things like remote, where you have to do an upgrade over an RF channel like Bluetooth or Wi-Fi. But if you're local, there's no point. So if I hit the cut, that's the Explorer board. That's the big Explorer board. I've got the meatball dropping down on the OLED screen. I've got something called Cylon, which is rotating back and forth a bunch of LEDs. That's off an GPIO expander, I2 GPIO expander. And then I've got the ring of NeoPixels blinking. And this is, I'm using millis as a system timer, so this is all happening at the same, well, in air quotes, the same time. So that's what I wanted to talk about. I could give you much more detail over at the Microchip booth because I'm running this demo over there. Does anybody have any questions about what I just walked through? And if not, then you can come see me at the Microchip booth later. I'm here all today and all tomorrow. Okay. All right. So if you're sitting in the 8-bit camp and you want to expand, you're kind of running out of power or speed with the 328s, with the Unos. With the Uno R3, I know Arduino released the R4 with the big Renaissance chip. But if you want to stay in the 8-bits and check out, like I said, as we bring the source level debugging online, I would invite you to check out some of the new parts. All right? Thank you very much.